Hello YouTube. In this video we're going to be discussing how to find specifically the determinant of a 3 by 3 matrix, but overall we've been discussing determinants of square matrices in general, and recall that a determinant of a square matrix is just some scalar or real number that is associated with that matrix, and that's what we're trying to find here. So the method you're about to see me use in this video here with 3 by 3s is actually not a general method. It's only specific to 3 by 3s, so please don't consider using this with something that's not a 3 by 3. So let's consider the following matrix. I'll define this matrix A as being this 3 by 3 matrix here that happens to be populated with the letters A through I, if you read left to right. But it says in order to find the determinant of this matrix, what we'll do is we'll start by recopying the first two columns of this matrix. So this would be this column here. We're going to take them and we're going to recopy them on the outside of the matrix, on the right side of the matrix. So it looks like this. So if we were to take this ADG, we're just going to copy it on the right side of the matrix here, ADG. We're going to copy BEH as well, which is the second column. And we see that we get this new matrix here. Now you'll notice that I've written determinant of A as DETA, which is this, it looks like absolute value bars, but bars around A, which is the bars around the original matrix. What we're going to be doing is this. We're going to say its determinant is actually equal to this quantity that you get when you carry out all of these calculations. But really what I'll point out is this. We say AEI really is the product of these three values right here. So we say AEI plus BFG, so multiply these three quantities right here, BFG, plus CDH. So we're going to take these three quantities right here and multiply them together. Now we're going to take the products of these three things, which we would get some numbers down here, this product, and this product. And what we could do is we could add them together and get some number. And that's what we'll do. And then once we find that number, what we're going to do is we're going to take away this whole quantity here. Okay. So we'd say this whole quantity here, really BDI. BDI is actually located right here. We say BD and I. We say also AFH, which are these three right here, plus CEG, which are these three right here. So if I had to break down in words what it is that you're doing when you find the determinant of a 3 by 3 is we recopy the first two columns on the outside, but it is the sum of the products of the main three diagonals minus the sum of the products of the three opposing diagonals. So sum of the products of the three opposing, if I can spell here, opposing diagonals. Okay, so we're going to use this scheme here to find the determinant of these two matrices over here on the right. But let's give this a shot. It says, all right, determinants of 3 by 3s, find the determinants of the following matrices. And you'll notice that I've already lined them up and called these matrices A and B. But I've lined them up inside these vertical bars right here, which would indicate we do want to find the determinant. So our first step is going to be this. We're going to recopy the first two columns. So we get 3, 3, negative 1. And we get 4, 5, 4. And the way this is going to look is this. When we carry this out the first time, we say the determinant of A. Might not be so bad to show our work here, but we get 3 times 5 times 1, which is going to be 15. So we get 15 plus. Now we'll do the next main diagonal, 4 times 0 times negative 1, which is just going to be 0. We might as well write this in a different color here. Plus now we'll do the last main diagonal, negative 2 times 3, which is negative 6, times a positive 4 is a negative 24. So we get this quantity here. Actually, I shouldn't have written that yet. I'd get that out of the way, negative 24. Now we're going to take all of this now, which was this first quantity, and we're going to subtract off now the product of the main, the sum of the products of the main, or the opposing three diagonals. So we now say, starting in this corner, 4 times 3 times 1, we get 12. Plus now, 3 times 0 times 4, we would get 0. Plus now, we say negative 2 times positive 5 times a negative 1, we get a positive 10. Okay, so we get a 10. So really, this determinant really comes out to be this. We'd say 15 and a negative 24 is a 9, negative 9. Minus now, 12 plus 10 is 22. So we get this value right here, we get negative 31, okay, when you add these things together. So negative 31 is the determinant of this matrix here. Okay, so let's try one more time here. We say we'll recopy the 1, the 3, and the negative 2. It's negative. We say 2, 1, negative 4. So we get the determinant here. We say determinant of B, which is the determinant of B this way. We'd say really is this 1 times 2, it's 2. Plus 2 times 0 times negative 2, which is 0, plus negative 1 times 3, which is negative 3 times a negative 4 is a positive 12. all of this now minus, now we'll go the other way, 2 times 3 times 2, which is 4 times 3, which is 12, plus 1 times 0 times negative 4 is 0, plus negative 1 times positive 1 is negative 1, times the negative 2 is a 2, so we get this right here. So in this case, we get the determinant to come out to be this. We get 14 minus 14, which equals 0. So this is actually kind of an important thing, but I re-mentioned this here. We say a matrix having a determinant with a value of 0 is referred to as being a singular matrix. Okay. So when we solve some more matrix equations, we're going to find that any matrices that have systems that have determinants of 0 in their coefficient matrix must have had equations that either canceled out perfectly or nearly canceled out perfectly, thus leading to systems having inconsistent solution types or consistent dependent solution types. Cheers.